good morning, everybody.
Good morning, sir.
Good morning.
Good morning, sir.
Okay, so let's begin. By the way, I think in one of the classes I had shown this video, but you said that you could not hear the sound, the audio. So this is for your reference. The idea behind showing this Iridium constellation video is mainly that uh, other than geostationary satellites being used for communication purpose, there are now also other kinds of satellites. Just a minute. Yes, so what I was saying is that the fact that other than geostationary satellites, low Earth orbiting satellites are also now being, used, not maybe in a big way, but with some success for the purpose of communication. But the commercial success for this kind of a constellation is yet to come. So let me share my screen. So can you see the screen now?
Yes, sir.
Yes, sir.
Okay. So I think in the last class we were calculating, we had talked about the elevation azimuth, the look angles, and we had also done few calculations. Okay, so today we begin with the condition for visibility of satellites. That is, as I was mentioning in the last class, that not all satellites launched from any location are visible from any point on the surface of the Earth. And because of that, there has to be some kind of a condition to be satisfied, for which a particular satellite launched from a location will be visible to an user. So if we just take a look at this particular figure, what we can understand that this is that we had earlier used for the elevation calculation like this. Only that the only difference is that now the satellite is at a much higher, kind of uh, position in the sky. So this is the center of the Earth. That's the Earth station, which is trying to uh, track that particular satellite signal. This is the satellite. So we can understand that this angle is between the radius of the Earth and the or local horizon at this point, because the local horizon is tangent or tangential to this point. So this angle is 90 degree, and the angle of the light is this one. That means the line joining the Earth station with the satellite, and that local horizon, the angle in between, that elevation angle. And this is the central angle, that means between the radius of the Earth and the line joining the center with the satellite. The included angle is what we had already learned in the last class. It's the central angle. So the calculation of this condition actually involves this estimation. If this is the radius of the Earth and this is the angle gamma, then this side, as you can see, will be Re by cos gamma, right? This, I think you can understand, this angle is 90 degree. So in this triangle, if this angle is gamma, then cos gamma is Re by this side. So this side will be Re by cos gamma. Now the point in calculating this distance up to the local is that, as you can see, the satellite is right at this point. If it continues far right, then there will be a time when, if you extrapolate this particular local horizon, the satellite will be below the horizon, right? So that means that will set a limiting condition up to which you can calculate or you can receive the signal from that particular satellite. That is why this corresponding value of Rs, this is Rs. So the limiting value of this Rs up to which the satellite signal will be visible, that means the satellite will be above the local horizon, that is given by this Re by cos. So that means for positive or zero elevation angle, because you can understand that when the satellite is aligned with this local horizon, the elevation angle, which is the angle between the local horizon and the line joining the Earth station with the satellite, so that line will also be aligned with the local horizon. So the elevation angle will be zero. But for receiving signal, it's fine. That means this Rs at that time, the limiting value of this Rs has to be greater than Re by cos gamma, because this Re by cos gamma, as you can see in this condition, that's the situation, or that's the condition when the line joining the satellite with the Earth station is coincident with the local horizon. So that condition has to be, this Rs value has to be better or higher than this Re by cos gamma. That means the satellite has to be on this side. If it is on this side of this extrapolated line, only then will the signal be visible, and the corresponding value of Re by cos gamma will increase, maybe to this or this or this or this level. So that means the underlying condition for this positive or zero elevation is that this Rs should be greater than equal to Re by cos gamma. So this inequation actually sets the the quantitative condition for which a particular satellite signal will be visible from an Earth station. So we can say that from this relation that cosine of gamma if we express that, that should be less than equal to RE by RS. So gamma should be less than equal to cos inverse of RE by RS. RE is the radius of the Earth. So this is the condition for visibility. Now, if you quickly put the value of RE and RS, okay, you know the value of the radius of the Earth and you know the value for of RS for a nominal geosynchronous orbit. So if you put those values, you will get a corresponding value of gamma, the central angle, as less than equal to 81.3. So could you just check, simply putting the value of RE and RS, whether you are actually getting this value or not?
Yes, sir.
Yeah, just check.
Yes, sir. I just checked. It is
Yes, sir,
81.
81.276 degree.
Okay, so this is for geosynchronous satellite. Now that we had seen in the case of Iridium that low Earth orbiting satellites are also being used in some cases. So could you please calculate the corresponding value of this gamma for a low Earth orbiting satellite? Say assuming the orbital altitude to be 1,000 kilometers or so.
30.13 degree.
Yes, sir.
Yeah. So what's your name, please?
Shromana Majumdar.
Okay. Ognisha Bhomik, have you calculated this? Ognisha,
Yes, sir, I'm doing it.
yeah, please let me know the value that you get. And also, please do that for a medium Earth orbiting satellite also. The
Sir,
visibility.
76.07
71.5.
degree.
Okay. So
76.070.
76.
Yes, sir.
I mean, what is the orbital altitude that you have taken?
Sir, 20,200 kilometers.
Yeah.
Uh,
Okay. Let some of the others please confirm these values for a
Yes,
lower
sir.
Earth orbiting.
76.7077.
Okay. Your name?
Sir, Som Kundu.
Okay. Shayan Datto, are you there? Shayan, Shayan Datto, are you there?
Yes, sir.
So what value have you got?
Sir, 76.14.
Okay.
Sir,
Ravi Kumar Thakur,
71.5.
uh, who is it?
Sir,
Yes, sir.
Shreyas,
Hello.
71.5.
Yeah, but who was speaking earlier?
Shreyas Roy.
Okay. And for lower Earth orbiting, what value have you got?
sir, 30.13.
Okay.
Yes, sir. 30.6.
Okay. Okay. So let's move ahead. So now that in the last class we had, calculated the elevation and azimuth of a geostationary satellite, uh, which is located, sorry, at 73 degrees east. That satellite is FleetSatcom, as I had mentioned perhaps in the last class. The name of that satellite, that is FleetSatcom. This satellite at 73 degree east from Kolkata, that is FleetSatcom. So, could you please test the visibility of this satellite from Kolkata? That means whether this satellite is, its signals could be tracked or not from Kolkata. Please check.
Yes, sir, that is visible.
What's the value of the central angle that you have got?
Sir, it's 0.84.
0.84 central angle.
Sir,
Sir,
27.57
27.
degree.
Sir, 32. Sir,
27.09.
32 is the central angle. I took roughly 0.84 is the cos inverse of that. Cos of central angle is 0.84.
No, you tell me what's the value of the central angle gamma.
27.09 degree.
Yes, sir.
Yes, sir.
Yes, sir.
27.09. Okay. So what's your name, please?
Sir, Shreyasri Roy.
Okay. Mousumi Mondol, are you calculating?
Yes, sir.
Yeah. So what's the value that you have got? What's the value of the central angle that you have got?
The 27.08.
So some of you are getting values of 27 and some are getting 32. Why is it so?
Sir, it was my fault. I did some rough calculations. I didn't take the precise value.
Okay.
Sir, it is visible.
Yeah, because the central angle is less than 81.3. So that satellite is visible from Kolkata, right? Now, moving ahead, uh, so far what we have considered, that is the orbital period, the condition under which a geosynchronous satellite becomes a geostationary. These are all under ideal conditions where, following Kepler's laws, we assume that in the mathematical formulation the earth and the satellite are point masses, and each is influenced by the gravitational attraction of the other only. There are no other additional forces or additional factors to take into account. But actually, the satellite and the Earth, this kind of a two-body system, I mean, it's not a two-body system only. That's the point. There are other factors which does influence the movement as well as the operation of a geostationary or a geosynchronous satellite when placed in orbit. Now, one of the factors to consider here, which we know actually, from a long time from our geography classes, perhaps in class 7 or 8, that the Earth is not a perfect sphere. In Kepler's laws of motion, we assume theoretically that the Earth and the satellite are essentially, point masses, because, or if they are perfect spheres whose center of mass could be identified at the center. So the real situation is not like that. The Earth is a kind of an oblate spheroid. Okay, triaxial oblate spheroid. As a result of this, what happens is that the gravitational potential, I think you may have read about this term somewhere in your earlier semesters or physics class, perhaps. Have you heard of this term, the gravitational potential?
Yes, sir.
Yes, sir.
So, conventionally or theoretically, the gravitational potential is, considered to have a simple 1 by distance, 1 by r dependence. But in case of Earth, one of the overriding factors which does not allow the gravitational potential to have this simple 1 by r dependence is the asymmetric distribution of mass. Okay, that is, within the surface of the Earth, actually, there are certain regions uh, where the density, the mass density is found to be more than in the surrounding areas. Those regions are referred to as mascons. Okay, these are terms which may be new to you, mascons. So as a result of this, what happens is that the gravitational potential of Earth does not have a simple 1 by r dependence, but rather it is represented in a series expansion of Legendre polynomials in ascending powers of this Re by r. Okay, that means the ratio of the radius of the Earth to the distance. Now, out of this series expansion, once again, the dominant term is J22. That is the second order term. And this actually, this non-dependence or not having a simple 1 by r dependence, this, sometimes causes an unconstrained geosynchronous satellite. We will come to this in a little bit more details in some of the next chapters, but here let us introduce these things to you, that a geosynchronous satellite or a geostationary, whatever, after launch, it has a typical lifetime of about 7 to 10 years. Because the major problems that occur beyond a certain period of time is that the power sources, in case of a satellite, which is almost always the solar panels on which the incident solar radiation falls and is converted into some kind of an electrical energy. So those solar panels, they age, and because the conversion efficiency of the solar cells are very poor, okay, even with a lot of advancement in technology of optical conversion to electrical energy, the conversion efficiency of the solar cells at the beginning of their lifetime is only about 15 to 17%. Only 15 to 17. That means more than 80% of the incident solar energy is wasted. So as a result, what happens is that with age, with time, the efficiency further comes down, and we have a situation that is beyond a few years of operation in orbit of a geosynchronous or a geostationary satellite. These solar cells, they suffer further, you know, uh, degradation, both in terms of their physical structure, because there are innumerable number of micro meteors which fly by always. Sometimes impact with them could be quite fatal for these satellites. So the energy source within the geosynchronous satellite, that gradually gets reduced, so that it is almost like a car moving down a inclined slope, and then it some kind of a malfunction of the brake of that car happens. So that car is then in a very precarious or dangerous situation. That means it is only it could be controlled up to a certain point. So that kind of a situation happens in case of a unconstrained geosynchronous satellite towards the end of its lifetime or after the end of its lifetime. And uh, we will learn later on that by virtue of this uh, oblateness of the earth, there are 4 points which are generated on the geostationary orbit or geosynchronous orbit, which are stable. Two of them are stable points, and other two are unstable points. So the stable points are, you can imagine that, as the name suggests, when an unconstrained geosynchronous satellite, that means a satellite whose kind of energy resources have nearly ended, and you cannot control the movement of that satellite using ground control commands anymore. So for that kind of an unconstrained geosynchronous satellite, what happens is that uh, these either of these two stable points, like one is located around 75-degree east, as you can see over here, and the other around 252-degree east. So one is primarily in the Indian or the Asian longitude sector, and this one is in the uh, American longitude sector. So these two stable points, they are naturally occurring points which act as some kind of a, you know, uh, attracting source. That means once an unconstrained geosynchronous satellite drifts near to any of these two stable points, they tend to circulate around those points only. Otherwise, what may happen is that they may move in an unconstrained manner and collide with other active satellites. So that would be catastrophic. So it is nature who has provided us with a solution to this problem by providing two stable points around 75-degree east and 252-degree east. Remember, these are not artificial or man-made. They are completely natural phenomena. So typically, these unconstrained geosynchronous satellites, every country which launches these satellites, they try to steer them towards one of these two stable points so that these unconstrained objects do not collide with, you know, um, other active satellites. And these points or these locations are sometimes referred to as graveyards of satellites. Okay, it is as if a place where the dead or defunct satellites are they are kind of housed or stored. So this has also given rise to a significant amount of space debris because you have to remember that humans have been successfully launching artificial satellites from about 1957, right? The first successful launch of a satellite was in 1957. So over the last, say, more than 60 years, there has been a launch of satellites. During the initial years, of course, the number of satellites was less, but starting from the 1980 onwards, there has been a lot of satellites which have been launched by different countries. So definitely over this period of the last, say, 40 years or so, the amount of space debris that has also gone up in a big way. The second effect, I mean, which also is kind of a natural phenomena, because you see this Earth's oblateness is not an artificial phenomena. I mean, humans have not made the Earth oblate spheroid. Nature has made it like that. And because of that, there is a tendency that uh, at the geostationary orbital altitudes, you have two naturally occurring stable points, and those stable points actually provide some solution to the problem of unconstrained geosynchronous satellites which are drifting without any control. The second of these natural effects is that arises because of the sun and the moon. That is, in Kepler's laws, we have classically assumed that the sun and the Earth and the satellite are the only two objects to consider, and each is exerting some gravitational attraction on the other. But actually, uh, the effects of the sun and the moon, that also is important in this case, because you see that the gravitational attraction of the sun and the moon, it causes the orbital inclination of geosynchronous satellites to change with time. One of the conditions that we had seen in one of the earlier classes, the condition under which a satellite becomes a geostationary is that its orbital inclination that should be zero. That means the orbit should be, orbital plane should be perfectly aligned with Earth's equatorial plane. So, because of this attraction of the sun and the moon, the gravitational attraction, because they are also massive bodies, so it causes this orbital inclination to change. So, ideally, the orbital inclination will be zero at the time of launch, I mean, at the time of placing the satellite in orbit, and that may change to nearly 15 degree after 20 years or so, or 25 years. Now, this is a theoretically calculated value. You can understand that no uh, artificial satellite could have an effective or active lifetime of 26.6 years. They are defunct well before that time. But even within the first, say, 7 to 10 years of its operation, which is considered the effective period of operation of a satellite, there will be some change. It may go from 0 degree to 5 degree or something like that. So, a change in orbital inclination at the geostationary orbit of, say, 36 or 42,000 kilometer actually from the center of the Earth. If you add the radius of the Earth to the orbital altitude, then that means that a 5-degree change, that may mean that the spatial displacement of the arc, that could be something like several thousands of kilometers. Why I'm saying this? Because you see that if we just consider this relation, suppose S equals to R into that angle theta, say, let me see where is theta. Theta or phi, anything, say phi. So in this relation, suppose if you consider the case that your uh, angle that changes by, suppose, from 0 degree to 5 degree, okay, and your radius in this case is equal to the orbital, so that will be equals to the radius of the earth plus, say, 36,000 kilometers. So when you have this kind of a situation, uh, we can easily calculate that it will be like close to 42,000 kilometer. Can you follow me? Can you follow this? That 36,000 plus the radius of the earth, so that's like 42,000 something. And if the phi is 5 degree, then this becomes how much? 42,000 into 5 simply, right?
Yes, sir.
So the angle, though, so the spatial displacement will be 42,000 into 5, which will be like close to more than 2 lakh kilometer at the geostationary orbit height, right? It is not at the surface of the earth, but at geostationary altitude. So we can understand that when there is a orbital inclination of the geostationary or geosynchronous satellite from its ideal value of 0 degree to something like, say, maybe 5 degrees or so after, say, 7 years or 10 years of operation, that means that's a significant amount of change. because as the orbital inclination changes, that means the entire structure of the satellite, that is also getting tilted, that is also getting inclined. So the direction of the antenna, downlinking antenna, the antenna which is transmitting the downlinking signal, that also changes. And when that changes, that means that uh, the satellite will not be able to, I mean, the downlinking signal will not be pointed towards the surface of the earth or towards the desired user base, right? So as a result, during the effective period of operation of a satellite, there has to be some, some measures taken in order to correct this. It is not that we could leave simply this thing to continue. That means the orbital inclination to change and then uh, wait for the consequences to happen. We cannot do that. So that is why there are additional rocket motors or thrusters which are present. So as a result, what happens is that these thrusters or rocket motors, they actually provide the satellite with some kind of a maneuverability. That means something is getting tilted, so you apply a rocket motor or a thruster which actually applies some force in the reverse direction so that the satellite could, counter this movement which is arising out of these natural forces. Now, because of these, these kind of factors, that is the effect of the Earth's oblateness and effect of the sun and the moon, there are, several kinds of science and technology challenges which are there in the space environment. And while we are, more familiar with space, that means we humans have gone a long way in space. Within the surface of the earth, it's a different ball game altogether. That means within the surface of earth, beyond a few hundreds of kilometers, I mean solid earth, beyond a few kilometers, tens of kilometers, we know almost next to nothing. Okay. Under sea, humans have gone a long distance down, thousands of kilometers, but not under the surface of the earth. Okay, that means under the solid rock, under the solid surface of the earth. So that is why the characteristics of these mass cons, their distribution, whether there is a geographical distribution of these mass cons or not, and how they actually affect the gravitational potential, these are things which are still not very clear to us. On the other hand, you know, uh, in space, humans have made great advancement, but at the same time, the space environment is also very, very challenging and very critical. So that's why right from the sun, as you can see over here, that right from the sun going through the, the different kinds of interplanetary medium or so, we have been able to put satellites like Discover, which are quite close to that of the sun. There is one point which is known as the Lagrangian point, where we have put satellite. In fact, Indian Space Research Organization is planning a mission named Aditya, which will be placed about a few millions of kilometers from the surface of the Earth. Okay, so that is exclusively meant for studying the different characteristics of the Sun. Then coming closer to the surface of the Earth, you have the geostationary satellites at some orbital altitudes. Then further down, you have the medium Earth orbiting satellites like GPS. And then close to the surface, you have the low Earth orbiting satellites. And there are different, regions through which all these satellite signals, when they are communicating with the ground station, their signals have to pass. Whether it is a satellite which is close to sun for studying some solar characteristics, or they are geostationary or GPS satellite, whatever, their radio signals used for communication has to pass through these regions. And believe it or not, the near Earth space environment, it looks something like this. This almost looks like, an extremely crowded place. Earth is at the center, and surrounding Earth, you can hardly see anything because of the large number of satellites which are there. As you go out, radially out from the surface of the Earth, the number density of the satellites, they decrease a little bit, but still they are plenty. Okay, so there are huge number of space assets which are there surrounding Earth, and some of them are for military applications, or I should say, most of them are for military applications. Some are for commercial applications. A lot of companies, they have their own satellites, or they are sharing satellites for different kinds of purposes, for different kinds of applications. The space environment hazards, other than those, which we have mentioned, the natural phenomena arising out of the non-spherical shape of the Earth, and also the gravitational attraction of the Sun and the Moon. All these features are there. In addition, there are several, kind of factors or hazards which affect the satellite in orbit. So, one of the interesting things is that because the orbital inclination of the satellites are, gradually changing as a result of this attraction of the Sun and the Moon, so the satellites which have stopped operation, their active lifetime has expired, but they have not disintegrated. Usually satellites do not disintegrate. There are some military satellites which are deliberately or intentionally destroyed by the country which has launched it, so that the military information does not fall into gets in the other countries do not get access to that. So other than that, most of the cases, these satellites, they kind of uh, change their orbital inclination, but they are not destroyed deliberately or intentionally, usually. So what happens is that over this present decade, starting from 2020 onwards to 2030, the geostationary satellites which were deorbited, that means deorbited means they become defunct or they were not active during these early days, 1966 to 1976, they will start returning. I mean, they will complete, a kind of a cycle of operation, a cycle of a change of this orbital inclination, and they will return to the geostationary orbits are built once again. So what it essentially means is that there will be an increased number of space debris in these 10 years, starting from 2020 to 2030, and at the same time in the subsequent decades as well. Because as you can understand, during 1966 to 1976, there were not very many satellites launched. In comparison, from say 1976 to 86 or 86 to 96, during these periods, the number of satellites which were launched were much more. So these are, some of the major challenges which are there, whether you are using satellites for communication purpose or for, navigation purpose like GPS. I think I will stop here today and let me have your attendance, please. Okay. So 301.
Present, sir.
Just a minute. Three zero two.
Present, sir.
303.
Present, sir.
305.
Present, sir.
306.
Present, sir.
308.
Present, sir.
309.
Present, sir.
311. 313.
Present, sir.
314.
Present, sir.
315.
Present, sir.
316. 317. 318. 319.
Present, sir.
320.
Present, sir.
321.
Present, sir.
322.
Yes, sir.
322. Hello.
Yes, sir.
So are you 322?
Yes, sir. 322.
Your name?
Sir, Arup Kumar Mari.
Okay. 323.
Present, sir.
401.
Present, sir.
402. 405. 407. 408.
Present, sir.
411.
Present, sir.
414.
Present, sir.
420.
Present, sir.
421,
Present, sir.
422,
Present, sir.
423,
Present, sir.
424,
Present, sir.
430,
Yes, sir.
431,
Present, sir.
432,
Yes, sir.
433, 435, 437,
Present, sir.
438,
Present, sir.
439,
Yes, sir.
440, 441, 442, Shayan Datta, Shayan Datta,
Sir, present. My mic was not open.
Ravi Kumar Thakur.
Present, sir.
Okay. Okay, so thank you. And
Thank you. Thank you, sir.
Thank you, sir.
Thank you, sir.